Hope you're all doing freakishly awesome. In this video, we will be taking a look at the Albumentations library. So for those not familiar with Albumentations, it is a Python library and a pretty awesome one at that, I should say, specifically for data augmentation. So the library can be used with deep learning libraries like Pytorch and TensorFlow. And in this video, I want to take a look at how we can use it for different tasks, so classification, segmentation, and detection. Then in the final sort of part of the video, I will show you a full example of how to use it with Pytorch. All right, so just talking about it from a Pytorch perspective, why should we use it? So there are three benefits, I would say, for using it. The first is that it is faster than Torch Vision on every benchmark. And then secondly, which I guess is also the most important one, is that it has support for more tasks like segmentation and detection, which is a lot harder to do in Torch Vision. And I don't remember the third point, so let's just move on with the video. All right, so to start off, I'm just going to show the images that we're working with. So we have an image of a cat that we're going to use. We have an image of Elon, and then we have a corresponding mask to that image. And then we also have a second mask to that same image. And we also have a data set for cat and dogs, which we're going to take a look at later on in the video. But so first of all, let's just create a file, and the first thing we're going to take a look at is how to do it for classification. So let's call this classification, and starting with import, we're going to use CV2. We're going to import Albumentations as A. That's how you normally do it. We're going to import NumPy as well. We're going to also, from utils, import plot examples. So that's just a file that I created beforehand, and it's not essential to sort of the transformations that we're going to do on the images, but it's just so that we can plot and see that they actually work. All the code is going to be on GitHub, so if you want the details of that, you can check it. But from pill, we're going to import image. All right, so first of all, let's load the image of Elon. So to do that, we can use CV2, which is what they sort of in their official tutorials or examples that they have, that's what they normally use. I'm more used to using pill, so that's what I'm going to use. So I'm going to do image is image.open images elon.jpg, and that's it. So for the transforms, it's pretty similar to Pytorch, but we do transform equals a.compose. And then inside, we do a list. And inside this list, we specify the transformations that are going to be applied sequentially. So first, we might want to resize the image. Then we do a.resize. We specify the width, maybe 1920, and then height 1080. Perhaps we want to do a random crop of that resized image. So let's do random crop. And by the way, I'm not going to show you, there are so many different transformations that you can apply. I'm just sort of showing you a couple of ones and the structure of it. And you can go to their website to check out for more augmentations you can do. But so for a random crop, let's say we want a width of 1280 and a height of 720. Perhaps we can also do some common like rotation. So a.rotate. We can specify a limit to how much that should be rotated. So let's say I don't know, 40 degrees. And then to these transforms, we can apply sort of send in a probability. So we can send in, for example, 0.9, which means that this transformation is going to be applied in 90% of the cases. All right, so in 10% of the cases, it's just going to skip that one and move on to the one next in line. So some other common ones are horizontal flip, and we'll send in a probability. And so as you can see, it's very similar to Pytorch. You know, this in Pytorch would be random horizontal flip, and that's, you know, the structure is very similar. So we can do vertical flip, maybe in less percentage, maybe 10%. Some other ones, we can do RGB shift. We can specify a shift to each of these, sort of changing the coloring of it. And the probability is default 0.5, I think. So no, it's maybe not. So let's set it to maybe 0.9. And let's say you would want to choose one of several data augmentations. You could do a one of, and then you can specify. So let's see here, you can specify the ones that you want to sort of consider having. So let's say perhaps we want to consider to do a blur. So we can do blur limit. And I'm not showing sort of going through each of how they work. You can read the documentations for that. But sort of saying that we have a blur and we can have a color jitter. So how this works is that one of these two augmentations are going to be chosen with a certain probability. So let's say it's a 1.0. So in 100% of the cases, one of these are going to be chosen, and then that they are actually going to be applied is with a probability of 50% or 0.5. So that's how that works, and you can sort of consider that you can build these pretty complicated data augmentation sort of trees of how you want to actually perform this augmentation. So it's quite general in that way. But all right, so let's just say we have those transformed. That's just an example. What I'm going to do now is I'm going to create images list, and I'm just going to first set sort of have that image that we uploaded from the beginning, or that we opened from the beginning, as in this list. Then I'm going to do for I in range of 15. So we're going to show 15 examples. And what we got to do, first of all, is convert this this image that we opened with pill to a NumPy array. So we're just going to do NumPy array of image. That's it. Then for sort of doing the transformations, all that we do is that we set maybe augmentations equals transform, and then we'll send an image equals image. All right, so pretty simple. Now from this augmentation, it's going to return a dictionary, and from this dictionary we have to get the image. So we maybe do augmented image is equal to augmentations of sort of the key image as a string. So then let's do image list dot append that augmented image. Then in the end, let's just plot those examples of that image list, and let's see how that looks like. So if we now run this, all right, so here we can see sort of some examples of how that looks like. One thing here is that, so, there's a color. I don't know if this is the color jitter or if it's the RGB shift, but something's changing the coloring. There's obviously a rotation involved. There's some horizontal flip. There's a vertical flip. So it seems to be working pretty nicely. One thing I think perhaps could be problematic is that when it's performing a rotation, you can see that it's doing it sort of outside of the rotation. It is doing a reflection of that image, which perhaps could be problematic. One thing you could just do there is for the rotation, you can specify border mode to be CV2 border constant. There's like a lot of different options here. But if we rerun it, then we can see right here that it's just going to be sort of dark constant value outside of the rotation. And so that's how you do it for classification. Let's move on and let's create one for segmentation. And so I'm sort of assuming a little bit that you're here because you want to use it in Pytorch. But in Pytorch, when you're creating your data set, you have your get item, and all you would change is that instead of when you do self transform of your image, you just gotta obtain that example from the dictionary that you get returned. So there's really not much change to generalize this, but we're gonna see a full example as well in the last part of this video. But all right, let's copy paste our code, because it's going to be actually quite similar for all of these examples. So for segmentation, we need to open our mask, obviously. So mask is going to be image.open images, and then I just call it mask. All right, so we have the mask. All we're gonna change now is we're also gonna send in, no, first of all, we gotta make that to a numpy array. So mask is numpy array of mask. And I'm not really sure if this matters too much, but I've seen people use as array of mask and numpy, I don't know, some other stuff as well. And you can use numpy array, of course. Not really sure if there's a performance difference here, but I would doubt that it matters too much. All right, so what we got to do first of all is send in that mask. So mask equals mask. Pretty simple, I would say. And then how to get that mask, we just gotta, let's copy that line and then augmented mask instead. And you guessed it, all we have to change is from that dictionary, let's now take out the mask. So let's add that as well to our image list. And I think that's it. We can rerun this code here, or we can run this code rather, and let's see how it looks like. All right, so for a couple of examples here, we see that there's been a crop applied, and the corresponding crop has also been applied to the sort of segmentation, the target label. And similarly, here's a rotation. The segmentation mask has also been rotated. And so, that's really nice. That's really cool. And all we had to change is really like 2 lines. And I don't know, if you ask me, that's pretty amazing. So let's now create one for detection. Or actually, one thing I want to show you is that you can also have sort of multiple masks for a single image. So let's say mask 2. And what we'll do is we'll change this to second mask. And then instead of doing mask equals mask, what we're going to change right here is to do masks equals a list of mask and then mask 2. And of course, we got to also convert that to a numpy array. But that's pretty much it. And now we should also obtain, let's see, a second mask. So we could do that augmented second mask, and then we'll append that to the list as well. So augmented second mask. And we might have to change this. So let's change it to maybe 4. And let's rerun it. All right. Just .jpg. All right, sorry. So what we got to do here actually is we got to do augmented masks, and then we got to get that by using masks when we're as the key, and then right here when we're adding that to the list, let's do augmented masks and then the zeroed element, and then we'll do the similar thing for the second one, but we'll use 1 right there. So hopefully this should work now. All right, and as you can see here, so at the top left, that's the original image. Here's the first rotated example, and I'm not sure, there might be some cropping involved here too, and so on. And then we can see that both of the masks, same transformations has been applied to both of the masks. And that is awesome. Pretty darn cool library. So what we got to do now for an example of detection, before we move on to showing sort of a full example in Pytorch, let's just copy paste or paste in that code right there. And what I'm going to do now is I'll show you how to do it with CV2 if you want to load images with that. So we'll do image cv2.imread, and then you'll do images, and then let's choose the cat example for this one. And one thing you gotta do as well is you gotta do cv.cvt color of that image, and then cv2.color bgr to RGB. And so from what I could understand, for some historical reasons, OpenCV loads the images as BGR instead of RGB, and that's what the format that we want it in. So all we got to do is just do this line right here. And now that we have the image, we're also going to have a corresponding bounding box. So we have bounding boxes, and in this case, I'm just going to put them in manually. But how you would do it is you would have a list for each of the bounding box in that image. So you would send a list of lists where each list has the bounding box. And here it's quite important to also know the format that your bounding boxes are in. So I guess for those familiar with object detection, if you're there's sort of some different formats. For Pascal VOC, you have Xmin, I think Ymin, Xmax, Ymax, sort of the top left corner and the bottom right corner. And then you have different ones. So YOLO, for example, has a different one where I think it has sort of the width and the height, and then it has a center point. And then you also have Coco, which has a different bounding boxes. So you gotta just know which one you're using. In this case, this is from Pascal VOC. So why it's important, let me show you. So here we're gonna use the transforms, but now we're also gonna send in bounding box params, all right? And all that we do here is really a.bounding box params. And here we specify the format. So here is when it's important to know. So we specify format is Pascal VOC. And if it's in YOLO, you would just write YOLO. If it's Coco, I think you would just write Coco. There's going to be a link to the documentation for that. But yeah, Pascal VOC. And then one thing we got to do as well is specify labels fields. We're just going to specify that to be empty. I'll talk a little bit more about that soon. But all right, so we'll remove this mask thing right here. We don't have to convert it to a NumPy array because we used OpenCV. And one thing we have to do though is rate a save the bounding boxes. And let's just do bounding boxes of 0. So we'll keep that original one as well. So those 4 values right there. And let's see what we got to change. So masks, we got to remove that. We don't have that anymore. And all we do here is we specify bounding boxes to equal bounding boxes. So pretty easy. And let's see. So we are appending that thing right there. And one thing we can do as well is save bounding boxes of dot append augmentations of bounding boxes. And it's going to return it as a list of lists. I just want the list in this case. So I'm just going to do of 0. But yeah, so if you have multiple, it would make sense. In this case, we just have 1. So that's why I'm doing it this way. It's pretty much just for the visualization that we're going to get when we do plot examples. All right, anyways, so I'm just going to send that in, save bounding boxes to that example in the utils files, in utils file. So let's run this example and let's see how it looks like. Let's do a couple of more examples. So let's do maybe 15. All right, so now we can see a couple of more examples. And as you can see, it's obviously following, the bounding boxes are following where the cat is located. One thing you might notice is that when we're performing the rotations, the bounding boxes become inflated, but that's a common issue, and so that's not an error. It's sort of just expected. Yeah. So I guess one thing here is that when we're using the random cropping, as you can see, sometimes the cat is not in the image anymore, right? Because perhaps that part was cropped out. So one argument we can also send in is something called the minimum area to this box params. So we specify min area to be equals to maybe 2048. And this is meaning that the bounding box area shown in the image should have at least 2048 pixels in area. And then you can also send in another argument that is min visibility. Yeah, so the minimum visibility here means that the bounding box should have, I guess, some area which was sort of with respect to the entire image. So it should cover some percentage of the output image, I guess. So in this case, I would assume that this means 30% of the entire image. I could be wrong there though. But so if we use those arguments and we rerun it, and yeah, so now what it's doing, as you can see, we got an error right here, and that is because now it will drop some bounding boxes. So specifically, we could make sure here that we could do, check if the length of the augmentations of bounding boxes, if that is empty, then let's just continue, right? Because then that would mean that the bounding box was dropped because it was too small for the image or something like that. So now we can see these examples which look pretty good. And yeah, so I mean, doing these kinds of if you were to code sort of just the rotation part and having the bounding box, that it would be tricky, to be honest, and it would probably take a lot of time. So having this kind of a library is super useful. And yeah, so let's create another example. Let's call it full Pytorch example. All right, so these are the imports that we're going to use: Torch, NumPy, OpenCV, Pill, and then Albumentations. We're also going to import 2Tensor v2 and then OS. And so for this sort of more complete example, we have a cat and dog data set. So we have a couple of images of cats, we have a couple of images of dogs, and I just want to show you a complete example of how we create a data set class and also how we can create the data loader. So let's create class. Let's call it image folder. And I guess for those of you who are familiar with image folder in Pytorch, we're just kind of going to replicate that one or create our own version of image folder. I guess you could send in transform as a function in some way, and you can sort of just use the image folder that's built in Torch Vision, I think. But let's just create it ourselves. Who cares? So let's do init. We're gonna have self, a root directory, and specify transform to be none as default. And then let's call super on that thing. So self init. We'll do self.data is empty. And so my idea here is that we're going to go through the folders in that the subdirectories of cat and dogs. And specifically, I want self.data to be sort of the image file. So maybe it's called cat0.jpg or something. And then I want the label with that one. So that would be 0 because it's in alphabetical order, it's the first folder. So that would be index 0. Maybe then we would have some more examples, and then we would have dog0.jpg, and then we would have 1 as label. And of course, we want to do this general, but that's what I want for the data. So let's just do self.root directory is root directory, self.transform is transform, and then let's do self.class names equals os.list directory of root directory. All right, so that's going to list all of the subfolders in the root directory, which is cat dogs. All right, so what I'm going to do here is for index comma name in enumerate self.class names. We're first going to go through, find all of the files. So the files, we're going to do os.lister of ospath.join of the root directory and the name. All right, so that would be cat dogs and inside cat. So we'll find all of the files included in that one. What we want to do now is want to add it to this list. And of course, there are probably much better ways of doing this. So if you have any suggestions of making this a little bit cleaner and better, just comment and we'll make it better. But so self.data, we're just going to do plus equals a list of zip of all the files, and then the index, and then we're just going to do that for the length of the files. So, you know, for the first one, it's going to be index 0. So it's going to, all of those files are going to be associated with a label of 0. All the cat images and then dogs are going to be labels of 1. So if you're not following completely here, that's okay. This could perhaps be done in much easier ways. But for the length, we're just going to return length of self.data. And then for our get item, so we'll do get item, we'll send in an index. So first we'll get the image file. So the image file, and then the label, we'll get that from self.data of index. Pretty easy. Now we just have to find that file. All right, so what we got to do first is just find sort of the root and the directory. So we'll do os-path join of self.root directory, and then we'll do self.class names of that index. Of label. So we'll get what the class name is for that example that was sent in. All right, so maybe that was a cat. Then we'll get cat dogs, and then this is going to be cats. All right, so to load the image, we'll do numpy array of image.open of os-path join root and directory, and then the image file. Okay, so now we'll check if self.transform is not none. We'll do augmentations equals self.transform of image equals image, right? And this is exactly as the example that we've shown in the classification example. And then we'll do image equals augmentations of image. All right, so what is the difference if you would also have bounding boxes and stuff? You would do bounding boxes equals bounding boxes, right? And then you would get those bounding boxes and you would return them at the end. And that's the difference, right? Similar if you had a segmentation segmentation task. So this, you know, it's quite general in that way. And in the end, we'll just return image comma label. And that's it. So I'm going to copy in some examples, or the example that we had previously. Let's maybe do the classification one. I'm just going to copy paste all of that and just paste it to our example here. All right, so what's the difference? Here there are just some small differences. First, we got to do normalize. So a.normalize. We got to send in mean. So let's just set it to 0, 0, 0. We got to send a standard deviation. Let's just set 1, 1, 1. And then we got to send in a mean or a max pixel value, and it's going to be 255. All right, so I think this is also by default 255, so you don't have to change send it in. But I think this is important to be clear because this is not similar or exactly similar to Pytorch. So in Pytorch, you would do to tensor, right? And then you would do normalize, and you would normalize with all of the mean values between 0 and 1, and similar for the standard deviations. That is also what you do in this normalize. So you would find out what the mean and standard deviation is, and all of those values need to be between 0 and 1. And that is because what is going to happen when we're doing this normalization inside that function. Actually, we can go to that function. So let's just see what it looks like. So I'm just following that example. And if we go to normalize, what is happening here is that they're multiplying the mean with the max pixel value, which is 255. So therefore, assuming that mean is between 0 and 1, similar for the standard deviation. And here they're just taking the reciprocal of the standard deviation because they want to multiply it instead of divide it. But so I guess what is important here if we go back, is that these mean and standard deviations are going to be exactly similar to how you do it in Pytorch, but you need to remember that when we're doing 2tensor at the end, that is not dividing by 255, which it is in TensorFlow, or Pytorch, sorry. All right, and so what we got to do now is, I guess, just dataset equals image folder of root directory. We'll set cat dogs, and then transform equal transform. And now, of course, you could just import to, you can, create this to a data loader, send in the batch size, number of workers, and it would work exactly the same. Just to make sure that it works for this data set, let's just do for xy in dataset and print x.shape. Just make sure that it works. All right, so as we can see, it's working. And yeah, I'm not going to show you the data loader, but it's exactly the same as how you would normally do it. All right, that's it for this video. Hopefully it was useful for you to sort of take a look at how Albumentations library work and how you would do this different tasks. So I just want to say thank you so much for watching, and I hope to see you in the next video.